In this video, we're going to talk about a generalization of Green's theorem. In that, Green's theorem can actually be applied to regions that contain holes, that is, regions which are not simply connected. So I'm going to go ahead and try to go through a partial proof here of how exactly this would work. So let's take an example maybe like the following. Maybe here we kind of have a region D. I can see that I have a positively oriented curve, C1. Okay, it's positively oriented. When I reach out with my left hand, I touch the yellow space. And notice that on the inside here, I kind of have C2, and it's marking out or enclosing a hole. But notice that it is still positively oriented because when I reach out to the left, when I'm standing on this thing and walking in this direction, I still would only touch the yellow space. So both these are positively oriented curves. Well, what we want to do is to try to figure out how I could actually determine if Green's theorem applies here. So on the next page I'll say, suppose that we want to find this line integral, where P and Q have continuous first order partials on a region containing the D. Okay? To do this, I'm going to divide up our region D as follows. So I'm going to go ahead and state that, well, let's suppose that I grabbed something like right here, and I went straight across like this. Okay? And then I went and I did the same sort of thing here. I just kind of draw a straight line and I cut right across this. Okay? So if I had these two lines in here, I'm going to go ahead and kind of define then some additional sorts of curves and spaces. First off, I'm going to refer to this upper region up here as D1 and this bottom region down here as D2, or I'm going to do them with primes. Okay, so it's D prime, D double prime, just standing for space 1, space 2. Now, I can also see that my curves got split. C1 I can now imagine as kind of having two portions. I'll refer to this top portion up here as C1 prime, and this bottom portion I'll change to C1 double prime. Similarly, I'll see that I'll change this C2 to be C2 prime, and this bottom portion to be C2 double prime. So notice I'm kind of dealing with these distinctions and separations that happened once I introduce these lines. Now I'll define this curve over here as C3, and I'll orient it this way, and I'll make this curve over here C4. And so once I've kind of added all these different things, I can go ahead and see a couple different pieces of things begin to pop up. So first I'll say, how about we let C prime be the curve made up of C1 prime, C3, C2 prime, and C4. You can almost kind of tell where this curve exists, right? So like notice if I started maybe over here at this dot and I moved in the direction of C1 prime, I'd move all the way along here, I'd go to C3, then I'd go along C2 prime, along C4, and I'm right back to where I started. This is kind of forming a boundary of D prime. Well, in the same way, I can go ahead and I can let C double prime be the curve made up of C1 double prime. I'll say negative C4, because I'm going to want to move along C1 double prime, reverse the orientation of C4, move in the direction of C2 double prime, and then I'd probably have to reverse the orientation on C3 as well. Okay? So I can see here that both of these are positively oriented, piecewise smooth, simple, and closed. Both of these individual pieces are. So here's what I'm going to go ahead and claim. I would claim here that if I want to do a double integral over D, the entire D, right? Sorry, let me rephrase that. Let's suppose I start by just focusing on the line integral at the start, which was over C prime. Then what I can do is to say that I know that if I was to do my integral over C prime, my line integral of my p dx plus q dy, by Green's theorem, I automatically know that this would be equal to a double integral over d prime, and I would have my partial q with respect to x minus my partial p with respect to y. Okay, I would definitely have that dA. But I could also state the same thing here kind of for c double prime. That again, if I set up my line integral, that would have to be equal to a double integral over my d double prime, that bottom space, my partial q with respect to x minus my partial p with respect to y. So if I could add these two things up, I could hopefully get the result that I'm looking for. So take a look really quickly. I'm going to go ahead and state that if I had the double integral over d of my dq dx minus my partial p with respect to y, that this here is certainly going to be equal to the sum of my two other integrals here. So the integral over d prime plus the integral over d double prime. Now for the sake of time, I'm going to go ahead and not actually write in all the information in here. We know that that's supposed to just be dq dx minus dp dy. Okay. But what we've seen is that each of these double integrals here can be translated back into their associated line integral. So I'm going to go ahead and rewrite out what that's going to be the same as. So I know this is going to be the same as the integral over c prime p dx minus q dy, and that would be plus the integral over c double prime of, p dx plus q dy. Okay. But I can begin to start to break these down as well, because I know that to go along the curve c prime, that's actually going along these four separate curves. So let me try to write out what this would be equivalent to. So here's going to be moving along my c1 prime. I know that that's going to be the same as moving along c1 prime p dx plus q dy. But then I would have to go along c3 p dx q dy. And then I would have to go along c2 prime, make that p dx q dy. And then I would have to go along c4 p dx q dy. So all of that is just for this piece here, this line integral along c prime. I broke it up into all four of its pieces. Now, in a very similar way, I could try to break apart the other guy. I'm going to have to try to squeeze this in here. This is going to be c1 double prime p dx q dy, and then an integral along negative c4 p dx q dy, and then an integral along c2 double prime p dx q dy, and then finally an integral along negative c3, and I have all of that. So this is getting really complicated, and I know my goal is to hopefully show that all of this could just turn into the one simple line integral over just c. Okay, but let's see what we come up with here. This is going to be a bunch of different integrals that are added together, but I might notice some things. Notice here that I have a line integral for c3, or along c3, and one along negative c3. And you might remember that the relationship between the line integral along its curve and the negative of its curve is that they produce opposite values. So these guys here are going to immediately cancel out. In a very similar way, I also have c4 and negative c4, and those guys are going to be able to produce opposite values and cancel out. And so if I kind of look at what I ultimately have at the very end here, if I was to kind of summarize all of this, is that I have that I'm moving along the curve C1 prime, also along C1 double prime, which, when I put those back together, is going to ultimately just look like just the curve. Let's see, if I move along C1 prime, and then I move along C2 prime, or sorry, C1 double prime, that's just the original curve C1. Similarly, if I move across C2 prime and C2 double prime, see C1, C2 prime and C2 double prime, that's just the curve C2. So ultimately, this kind of turns back into, this is just the integral p dx plus q dy along C1 plus the integral for C2 p dx plus q dy, and all of that is really just the same as the curve C. So remarkably, even though I have this whole, if I can kind of break up these different pieces, I can see at the end of the day that what I'm really left with is still this important connection between this double integral over the region and the line integral that I have. And Green's theorem is still preserved, and Green's theorem holds on regions with holes. So, Green's theorem still holds for regions with holes. This is really, really awesome. And we'll see how we can actually begin to use this on example 5 in the next video.